Let's go through the 1499 max value equation. For this question, it gives us a two-dimensional array points. For each element, the point have an x value and a y value, which represent x axis, y axis, and also give us integer k. And it let us to find uh, 2 points, xi, yi, and xj, yj. And the index I smaller than j, right? And we need to maximize this kind of equation, that is yi plus yj plus the absolute difference between xi minus xj. It says that the points are solid. Those points are actually sorted by x values. So let's say if xi is smaller than yi, right? Then sorry, xj, then this part is a negative value. So what we are looking for is to find a maximal value with yi plus yj minus xi minus xj, right? So that is, let's change this formula. That is xj plus yj and plus yi minus xi, right? So we are trying to find those kind of 2 points which have maximum value of this, right? So we'll say I is smaller than j. So what we're thinking about is that every time because the points is already ordered with x, right? So every time we have a point, we looking in the previous points, the maximal value of the y. For example, this point is x and y, right? On the previous value, the maximal y exp exponent minus x, yeah, exponent, right? So intuitively, what we think about that, if we go through every points, then we brute force to go through those kind of previous points, get the maximal this value, right? That will be an O(n) squared time complexity. Um, but uh, but uh, uh, but the thing that this one has 10 to the power 5 range. So brute force way to check the greatest one is not doable, right? And there is another constraint is that for these points, um, they need to have the difference xi and xi minus xj, the absolute difference smaller or equal to k, right? So that means for those points, we are not looking for the previous biggest one. We are looking for the previous biggest one in a window, right? So that window is controlled by the x values. So we know the x epsilon with current x, they must have differences smaller or equal to k, right? So this will be a sliding window. Um, and the window, the element on this kind of window will be controlled by this x difference with current one, right? So if there is no constraints that the x difference is smaller or equal to k, right? Of course, we can use a previous max variable to store the y minus x, right? But there is a x constraints. This is a sliding window max. So we know use monotonic Q, it is an efficient way to find the sliding window max, right? So here is how do we analysis this question? Is that every time we have a point have X and Y coming, right? We need to find the previous Y epsilon minus X S epsilon, the largest one in this kind of window, right? So if we have a data structure store the maximum value, which can we can find the maximum value of y minus x in some kind of window, in some kind of efficient way, right? We can, for example, if we have this kind of data structure, we can check. We can just get it out and add to our current x plus y, right? And this will be a local candidate with we can compare with our global result. Um, and so this data structure is used to calculate the maximum value of y minus x, right? So the things that so that the step is that when there is new new point enter into our data structure, firstly we check this kind of data structure on its left, right? Whether those kind of points are out of bounds, if they have difference with current x is greater than k, right? We should pull them from the left. And after polling, if there is data, some point left in our data structure, on the top, that will be optimal one, right? The biggest y minus x value. So then add current x plus y. That will be a local candidate. And after that, what we need is that for our current point, right, we look at in this kind of data structure, those kind of combinations of y minus y epsilon minus x epsilon with current at this point y minus x, right? So if those kind of values are smaller or equal to current y minus x, right? That means those points have a smaller index and also smaller y epsilon minus x epsilon. So it will never be used anymore for later calculations, right? So that means those kind of index we can safely pull out from the right, right? So we need a data structure we can pull from the left and also pull from the right. Pull from the left is checking those kind of x bond, right? That will be smaller or equal to current x minus k, right? So for those smaller than x minus k, we'll pull from the left. Pull from the right is get rid of those kind of data which will not be used for future calculations, right? Here, there is one thing we need to be very careful about when to have a local candidate. Is that we pull from the left, those kind of out-of-bound candidate, and then the order is that pull first, we pull first from the left, which have the x difference is smaller than k, right? Then current k x minus k. Pull lots of points out. Here we need to use while loop because those points they are not consecutive. And then the second step is for current point, and we pick another this point from this data structure because that will be the largest y epsilon minus x epsilon in the range. and plus X and Y, and compare with the global result. The third step is we pull from the right. We cannot reverse these two steps because as long as there is data, right? Even in this data structure, we should have current X and Y and Y X epsilon Y epsilon as one of the candidates to compare with our global values, right? And um, if we pull from the right first, it is possible current XY will get rid of this kind of X epsilon Y epsilon combinations. So we miss some kind of candidates. So let's write code for this. So we need a deck, right? Deck. We put use deck to store those kind of index. So we'll have int n equals points dot length and result because we want to find the max value of the equation. So let's set the minimum value, min value first. So what we do is that for int I equals to 0, I smaller than n, I plus plus. So we are going to have int current point, right? Equals points I 0 and y equals points I 1. So what we do is first we need to get rid of those kind of points which is auto bound. So here, we'll see this point is actually not a consecutive, right? So so user if clause is not enough. So we need a while loop to get rid of those x has difference greater than k. So what we do is that while this deck is not empty, and x minus points deck pick first, right? Pick first, and this is its x values. If it is greater than k, right? Then we need to have deck for first, get rid of this kind of point. Then if there is data in our deck, we need to compare with our global result. Let's have int j equals deck pick first. So our result will be next dot next result and points J1 points J1 minus points J0, right? So this one will be the maximal one which have the largest y minus x, right? And plus our current point x plus y. So we need to check here, right? And then pull from the right those kind of useless the index. Because when we pull from the right, it is possible we pull the j point out, right? If we write a while loop before this, if we may missing some kind of candidate. So I write here while this deck is not empty. And points deck pick last. So we'll say this y minus deck pick last. This x, right? if this one is small equal to current y minus x, so these kind of points will never be used in the future calculations. So we can safely pull those kind of points from the right hand. And we'll see for this. So that means that we'll see we well those kind of data which is kept in this kind of data structure will be some kind of decreasing orders, right? So only if in the previous there is equals or great or smaller, we are going to pull them out, right? So um, so this will be a decreasing uh, deck. And in the end, we need to push the index at last, right? So here, you see that it's granted that there exists at least one pair of points that satisfy this condition. So we don't need to check if result equals mean value or not, right? So we just need to return result. And also let's write Python code for this. So we need to have from collections import deck, right? So we need a deck and result and also have length, right? Result will be because we are finding the maximum value, so let's have a minimal value. And this n will be its length. So what we write is for I in range. And so we're going to have x, y equals points I 0 and the points I 1, right? So we'll say why this kind of we are have this slide window for those kind of x difference to current x greater than k. We'll get rid of this kind of older points, right? And x minus points um deck. So this deck zero, this is same as peak. This one. If it's greater than k, right? Autobind, then we can have deck dot top left. So here we'll say if the deck um is not empty, right? So we need to check, right? Because here it doesn't guarantee it will not get those kind of um it does not guarantee there is any for every points. It will have points in range left, right? So we need to check this kind of deck is not empty or not. Of course, in the end, we can just write a return result. So result equals max. Um, it says that it's granted that there exists at least one pair. It just means this one will at least be true for some of the for one of the index, right? Result points. So we know the top one, right, has the greatest y minus x combinations minus points deck 0 there plus current x y. Now we need to pull from the right side those kind of useless points. While deck is not empty and the points deck. So that is the last one, right? Minus deck. There. As long as it is smaller equal to current minus x, right? Then we can get rid of these components. Get rid of these kind of points, right? So we can have a deck that pop in down in the deck append this in current index, right? And we need to return result. So doing like this, we'll see we have an efficient way to find those kind of sliding window max, right? And because every point is entering this data structure once and pull either pull from the left or pull from the right once. So the time complexity will be O(n), right? And the space, the worst case is that because this is a monotonic decreasing queue, right? Mm. Is this monotonic decreasing? Let me see. And if it is smaller, right? So it is a monotonic tonic decreasing. Um, if all of that being put on the queue, right? So that we may have the n element index in the deck. So the space complexity will also be ON, right?